Today we're going to start talking about plate tectonics. The logical place to start is at the beginning, which is known as continental drift. Depending on my class, this is either Unit 3 or Unit 10. Here are the unit level outcomes, which are the same for both of my classes, so you should pause the video and write these down in your notes. Here are some things I want you to think about as we talk about plate tectonics. If the Earth's crust is broken into moving plates, what happens if those plates move apart from each other? Do we get a big hole in between? Is the Ring of Fire more than just a Johnny Cash song? How is ancient climate information preserved in rocks? And what does that tell us about the location of continents in the past? Why is Hawaii an active volcano? Is it because it's near or on a plate boundary? Things to think about. Okay, so let's start out with a definition. What is plate tectonics? Well, I have a globe in this picture here, and the idea is that the surface of the Earth is broken into these plates that move around horizontally relative to each other. And one important thing to realize is that the plates are not necessarily the continents. That's an idea that was misunderstood in continental drift, and we'll eventually explain that detail. So here's a definition that you can write down. Now, what I like about plate tectonics is that it explains lots of features on the Earth's surface. It explains the global distribution or the location of mountain belts, active volcanoes, faults like your friend, the San Andreas Fault, earthquake locations, and it also explains features that are on the seafloor. So what is this idea, continental drift? As shown in this cartoon, the idea was that in the past, all of the continents were together in a supercontinent, and that since that time, those continents have drifted apart from each other to their present configuration. So here's a definition. Now, how did people figure this out? Early on, when people were sailing through the world and making maps of the continents, they realized that some of the continents seem to match up if you put them back together. And one of the more obvious ones was the South American and African continents that matched up if you put them together across the Atlantic Ocean. So you can write this down if you'd like. Let's take a closer look at these two continents. What you'll notice here is in brown, a little bit of overlap if you put these continents together. In this peach color, a little bit of a gap. So it's a pretty good fit. There's another color here, though, that I want to point out, and that's this light blue color. Because today sea level is relatively high, a lot of the continental margins are underwater, they're flooded. And if sea level were lower, the true edge of some continents would actually be farther out. So for South America here, if sea level were a bit lower, there'd be a lot more real estate down here that would be above sea level. The true edge of South America's continent is out here. We call that the continental shelf. And I point that out because we're going to come across that again in the future, but also because if we're going to match up continents, we need to match up the true edges of the continents. Continental drift was an idea put forth by Alfred Wegener. In 1915, he wrote a book called The Origin of Continents and Oceans. His idea was that there was a supercontinent, and the supercontinent existed about 200 million years ago, and he called it Pangaea, which means all land. It was surrounded by a single large ocean, right? If you have one single continent, then the rest of the world is an ocean, and he called that the Panthalassa Sea. You don't need to know the name of the sea, but I would like you to know the name Pangaea. Here's a picture of today's continents, and here's a picture of what he envisioned Pangaea to look like. The Panthalassa Sea would be all around it. And the Tethys Sea is kind of interesting because it's what becomes the Mediterranean. This is a little bit more modern view of what Pangaea might have looked like about 200 million years ago. And remember, 200 million years ago was fairly recently, geologically. It was actually around the beginning of the Jurassic. So this is when dinosaurs started to take over and really dominate the continents. So let's look at evidence for continental drift. And I'm going to make a list here that you can make in your notes. So the first piece of evidence we've already talked about is the puzzle-like fit of the continents. I showed you South America and Africa, but also North America nestles in there as well, as does a lot of Eurasia. A second thing that matches is sequences of rocks and mountain belts when you put the continents into their Pangea configuration. For example, if you look at this figure on the left, different colors here indicate different rocks. It doesn't really matter what their age is or what their type is, but when you put the continents into the Pangea formation, you can see that these belts of rocks seem to be continuous across areas that are now widely separated. Notice that the continental shelf is included here in the blue color. On the right, we have a little more detail of what was going on in the North Atlantic area. We have the Appalachian Mountains of North America, the Atlas Mountains of Africa, numerous mountains in Greenland and parts of Europe. These all formed an enormous mountain belt that was apparently higher than the Himalayas. Number 3, glacial evidence. This one requires a bit of explaining. There are two kinds of glaciers, alpine glaciers and continental glaciers. We have a lot of alpine glaciers on Earth. Those are the glaciers that are in mountains, and they grow a little bit bigger in winter, melt a little bit in summer, and they're fairly small and they tend to follow canyons. Continental glaciers are miles thick. They're enormous. They're what came in during the last ice age. And the only two continental glaciers that we have left on Earth are in Antarctica, which is shown in this picture, and in Greenland. And of course, you probably know that these are melting. In any case, these are such huge, enormous structures when they move that underneath them, they kind of polish the land surface. And so here's an example from Canada of a polished rock from the last ice age. And if you look carefully, you can even see grooves that tell you the direction that the ice moved. Now, it's not the ice that's scraping the rock, but locked into the ice is lots of other bits of rubble and rock. And so it's like sandpaper going over the land. And so what Wegener saw was evidence from Pangea time in all of these locations for continental glaciers. So he saw it in areas south of the equator, here's the equator, and north of the equator, and the arrows are showing the direction that the ice seemed to move. Well, this is very puzzling because if you have glaciers south of the equator, north of the equator, and at the equator, you would imagine the entire world should be glaciated. And there's no evidence for that. However, he put the continents back into the Pangea position, and lo and behold, we have what we would expect. An ice sheet centered on the South Pole and radiating outwards as we know continental glaciers move. So this was another piece of evidence that Pangea did exist. There was additional climate evidence in addition to the glacial evidence. This is shown in this picture. So we have the glacial evidence here, but then preserved in rocks, we have evidence for deserts at 30 degrees north and south, which we have today as well. There's reasons because of our wind patterns that we have dry conditions at 30 degrees north and south latitude. And then we have tropical conditions with limestones and corals at the equator. And so these are preserved in rocks, and they tell us that the equator in the past was not where it is today. So this is additional evidence that the continents have moved. Finally, the distribution of organisms, plants and animals, fossils. The one that's most commonly referred to is the Mesosaurus. This was determined to be a freshwater organism, and it was a reptile. It only existed in the Mesozoic, and then it went extinct. And the only place that this fossil's been found is in these two locations, South America and Africa. So it seems logical that these two places were once together. Because it was a freshwater organism, it couldn't swim across the salt water of the Atlantic Ocean. And here are some other distribution patterns of other fossils that are found in areas that are now today widely separated. This little box over here kind of sums it up. These creatures could not migrate across oceans. And by having all of the continents connected, it explains the distribution that we see today. Now, there were many people who did not like Wegener's ideas and didn't believe him. And so they had to come up with explanations as to how these organisms got distributed. There was the rafting idea, where the organism clung for its life to a piece of wood and floated across the entire Atlantic. Fairly unlikely. And then how is it going to populate the new location? The island stepping stones, you get the horses jumping just enough distance for them to jump from stone to stone. Definitely no evidence for that across the Atlantic. You have the Isthmian links, which are land bridges that are exposed when sea level is a little bit lower. And there are places where these things exist, such as between Kamchatka and Alaska, but they do not exist across the entire Atlantic Ocean. And then these critics also didn't like continental drift, so here they have two dinosaurs crying, their hearts are breaking, etc. Also, certain organisms have evolved separately in different continents. If you look at these organisms, you could probably figure out which continent they come from. These are all unique to Australia. So, for example, kangaroos are marsupials, and we have marsupials in North America. They're possums. So they've evolved in different directions. So even organisms today give us evidence that there were once connections and then things have evolved in different ways. Coming up next, what was Wegener missing in his continental drift theory that made so many scientists critical of his ideas?